So imagine a phase change of a substance such as water. And when that water, liquid water, is vaporizing and turning into a gas, those particles are gaining energy so that they can overcome intermolecular attractions and uh, break those attractions and turn into the gaseous state. So that process requires energy. So vaporization and other phase changes such as melting and condensation, there's an exchange of or change in energy. This amount of energy can either be classified as endothermic or exothermic. So in this data table, you have three substances listed. You have copper, water, and methane, and their respective amount of energy required to undergo that phase change. The unit for all of these are in kilojoules per mole, so it's the amount of kilojoules for every 1 mole of the substance. So if I look at the first column, it says heat of fusion for these substances. And notice that these are all positive values. Now, heat of fusion is the heat of melting. Fusion is another way we say melt. So think about the melting process. The particles have to gain energy to become a liquid. So during that solid state, those particles have to gain the energy to break some of those attractions between them. So if I look at all these heat of fusion values for melting, they're all positive values because melting is an endothermic process. But what the complete opposite of melting is, or its counterpart, is freezing. The amount of energy involved with freezing 1 mole of a substance is the same amount of energy involved with melting 1 mole of that same substance. It's just that freezing is an exothermic process because those particles are slowing down, they're losing energy. So the quantity of energy for all of these is still the same value as they're melting, but we're going to throw in a negative sign because it's exothermic. So copper has a heat of freezing value of negative 3.2, water negative 2.26, and methane is negative 0.946. Again, the amount of energy between freezing and melting, it's the same quantity, but it's just we use different signs to indicate if we're gaining or we're losing energy. In other words, is it an endo or is it an exothermic process? Heat of vaporization is the amount of energy needed to vaporize the substance from a liquid into a gas. And again, we have all positive values because vaporization is an endothermic process. But if you note here, their heat of vaporization values are much larger than their respective heat of fusion values because vaporization, turning a liquid into a gas, requires breaking all attractions between the particles. And that's why all of these substances have a higher heat of vaporization value than their heat of fusion value. Because in fusion, you're breaking some attractions, but in vaporization, you're breaking all attractions, which is going to require a lot more energy. The counterpart of vaporization is condensation, turning a gas into a liquid. This is an exothermic process. Just like before, though, we're going to have a negative sign and the same number, though. So negative 322, negative 40.7, and negative 8.61. Again, same amount of energy involved. It's just that we're losing that quantity of energy. So to indicate a loss, we put a negative sign. So let's try an example here. Number one, how much heat is required to melt 56 grams of copper? So I'm asked to start with 56 grams of copper and to solve for heat, which is energy measured in kilojoules. So I'm going to use the correct delta H value from the data table. So first of all, I need to look at copper, and I need the value that's associated with melting copper. Melting, remember, means fusion. So I'm going to look for the heat of fusion value from that data table and record it. So our heat of fusion for copper is 13.2 kilojoules per mole. So what that really means is for every 1 mole of copper, we're going to need 13.2 kilojoules. 1 mole of copper equals 13.2 kilojoules. So we take our start, 56 grams of copper, and we're going to convert this over to kilojoules. But my delta H value has the unit of mole in it, so I need to first convert my grams of copper into moles of copper. Molar mass of copper, 63.55 grams per mole. Grams cancel out. And now we're going to convert our moles into kilojoules using our delta H value. 13.2 kilojoules is equal to 1 mole of copper. Moles of copper cancel. You are left with kilojoules, and you finish up that calculation. 56 times 13.2 over 63.55. And we get a value of 11.63 kilojoules. Let's try another here. Number 2, I want you to hit pause and you try first on your own and then come back and check for your understanding. Okay, welcome back. So hopefully you tried this one on your own. Now we're going to see how well we understood this process. We're taking our start of 56 grams of copper. They're asking again for me to solve for kilojoules, heat, but this time they changed the phase on me. We're looking for vaporization. So I want the heat of vaporization value from the data table. So we're going to, vaporization. Look for the heat of vaporization value for copper. Scroll back up here. Copper has a heat of vaporization value of 322.1 kilojoules per mole. Paying close attention to my units. 322.1 kilojoules for every 1 mole. So here we go. 56 grams of copper. First convert that over to moles. Then use the heat of vaporization value of copper. All my units cancel out except for kilojoules, which is exactly what we're solving for. And now I finish up the calculation. I get 283.83 kilojoules as my answer. All right, let's try another one. The question reads, is 78 joules enough heat to melt 98 grams of ice? Justify your answer with a calculation. So now we're talking about ice. We're switching over to water. And our start value is 98 grams. This is a unique question. It's really 2 questions in one. First of all, here's the scenario. You have 98 grams of ice. We apply 78 joules of energy. And the question is the ice going to melt? And we got to figure out, well, how much energy is actually needed to melt 98 grams of ice? So that's our first calculation. You need to calculate the amount of heat needed to melt 98 grams of ice. So we're melting, we're dealing with fusion. We want to look at water and the heat of fusion value for water. Water is 2.26 kilojoules for every 1 mole. So we're going to take our 98 grams of ice and convert that over to kilojoules. 1 mole of H2O has a molar mass of 18.02 grams. Grams cancel. Then convert over to kilojoules, 2.26 kilojoules for every 1 mole of H2O. Moles of H2O now cancel, and you have kilojoules. So we quickly calculate that. 98 times 2.26 divided by 18.02. 12.29 kilojoules, okay, are needed. And so remember what the original question is. Ultimately, I need to answer with a yes or no. Is 78 joules enough energy to melt 98 grams of ice? If now we know 12.29 kilojoules is needed. In order for me to compare the amount available, 78 joules, to the amount needed, 12.29 kilojoules, they have to be the same unit. So I need to convert my joules to kilojoules, or vice versa, whichever one you choose, but you just have to compare apples to apples, not apples to oranges. So you have to compare joules to joules or kilojoules to kilojoules. So I'm going to choose to convert my 78 joules into kilojoules. I remember that 1 kilojoule is 1,000 joules. So we really have 0.078 kilojoules available. And now we're going to compare that value. Okay, and this is why writing units in your work is so important, because if before you didn't see that these were different units, you wouldn't be making a valid comparison. But now I can compare. 12.29 kilojoules are needed. We only put in 0.078 kilojoules. Is that enough energy to melt all this ice? The final answer is no. That is not enough energy. Not all of the ice will melt.